Thank you for the kind introduction, and yeah, I hope I will not take too long and it will be engaging. So I will talk about the work I've done the last couple of 8 years, so it's been quite a while. And I almost entirely always worked on the stability of lead halide perovskites, often in devices, but also studying just the films lately. And lately I've been going more into the in-depth characterization, so it's been more of a focus. And I just wanted to start with like some motivation which has kept me going. And I think it's important to always remember in some ways that 2024 was the warmest year on record. So we have seen a very steady, so the pre-industrial era is defined from 1815 till 19. And you see that very consistently every year, the temperature has been the average record, the average temperature on the world has been increasing. And last year it has been the first time above the 1.5 degrees limit of the Paris Agreement. So we wanted to limit ourselves. This is not too surprising. So already in 2018, people have predicted that this would happen with an 80% probability. But it's nevertheless a warning sign that we are on the edge of where we wanted to stick, and we should invest and work on this. And one really good way on working on this is solar. So solar has by far some of the best mitigation options if you change an energy production towards it, better than basically any other technology form. And solar is reaching its theoretical maximum efficiency. So further enhancement or like further development of this technology can only be happening if we combine it with other solar materials. And lead halide perovskites really have been like some of the best examples and best junctions we have been seeing so far, and working with silicon, the main market leader. But yeah, the big issue with metal halide perovskites is the stability. I think as most people nowadays know. And so my talk will entirely be about the stability of this material and how we can hopefully solve this and make it more stable. And for that, I am a physicist, so for me it really helps if I have a definition, and so I looked into this. And so the structure of my talk will be that I first talk about how stability is defined for photovoltaics. I will talk about the IEC 61215. I love the numbers for that. Then I will talk about how long perovskite solar modules have to last. So I did some cost calculations to get those numbers out. And then I will talk about the fabrication methods, which I've developed in my PhD, which have been giving me, in my work, so much better stability than other routes we have been using in just the perovskite. And then I will introduce a novel concept, sort of a new approach for surface passivation, and that's a dynamic passivation. So first, a bit of more important clarifications about the IEC and the IEC 61215. So any PV module will have to pass the IEC 61215 if it's sold on the market. So what they do is the manufacturer has to get the certificate from someone like TÜV Rheinland. And so they will ask them to certificate their modules, and they will then take a couple of random modules from the manufacturing line and then study those modules and go through it. And then in the end, if they pass, they will get a certificate that they passed this test. And these stability standards change over time. So I've written a review about the stability standards from 2016 for photovoltaics. But now in 2021, there was a new one published, which has some small modifications. And they're continuously adapted for failures for the PV modules in the field. So as we speak, people are doing research on this and studying the failures. Laura Schellhaus is already doing this in the US on perovskites, and other people around the world are working on this as well, and they're working together and publishing this. So there will be new tests, and there will be specifically also new tests for perovskite photovoltaics coming with time. So in a couple of years, we might see a specific standard. So this is then a subcategory of the IEC 61215, which will define additional stability standards, which will have to be passed for perovskite PV. So they will have to pass the IEC 61215, which already exist, but also new tests, which will be developed based on what failures they observe in the field. So this is the stability standard from 2016. So here you have those 12 modules randomly taken from the manufacturing line. They first undergo a series of small tests, and then they are split up into a sequence of different tests. And that is sort of like a thing which has been like often a little bit confused in publications. So sometimes they say, for example, oh, we passed the thermal cycling test. But there are two important differences. One is that they often only measure single cells and never modules. And often they only do a single test, but they don't do the whole series of tests from the beginning till the end. So it's not only about the efficiency of the modules, but you actually also have to do like a couple of other tests, like are they insulating still? Is there current leaking from them or something? Is it still safe to test them? So safety is a big concern in these tests. And yeah, the IC defines a loss of 5% as the minimum acceptable loss during those tests. And then industry takes these tests and they even do it sometimes like 5 times in a row to really make it more severe, to test their severity. And yeah, this is not really a guarantee for how long they should last. So sometimes people say, you know, if they pass it, it lasts for 25 years. But those are all extrapolations. And this is just based a test for after they've seen how they test the failures they've seen in the field. So there's not really a guarantee of how long they will last if they pass this. To give some summary of things people have seen or like developed, to give one example, for example, I can talk about very severe degradation people have seen for silicon solar cells. And here there are a couple of failures and they've been sort of categorized for how often they happen and how severe they are. And you see that hotspots, so if the cells go into reverse bias, is very severe and has been very happening. That's already been a while ago and people have been getting better at this. So here you see, for example, what's happening. Here you see a photovoltaic installation and there's a little bit of grass which goes over the last cell. And because of the shading, the cell goes into reverse bias because the cell doesn't have enough light and the current still goes through it in series. And then it goes into reverse bias and all of the energy goes into it as excess heat. And that causes this cell to be significantly hotter than the rest of the cells. And luckily, the PV community around perovskites also has been taking this more serious. In a couple of last years, there were a lot of like very nice studies also on the reverse bias stability. I do still think that this is a big issue, but hopefully we can find a solution for that. And as I said, there are various degradation factors, like this one, for example. This is, for example, some goats which are running over the solar cells, you know, because it's nature, so you never really know what is happening. So that's what we have to think about when we think stability. It's not really clearly defined as efficiency, but rather it's a very broad category of what PV solar cells will have to face. And the IC tries to tackle this by sort of like, you know, they measure failures in the field, they update the standards, and then solar manufacturers have to pass this standard. And on the second standard part, I will talk a little bit about how long perovskite solar models have to last. So this is not a simulation, this is a calculation. So this calculation is based on 3 factors. It's the cost, the manufacturing cost of the PV module. So if you compare it for silicon, this is around 30 cents per watt for silicon. And perovskites in most literature are probably lower than this if they get to the, like, if the economy of scale works for perovskite. So that's an important assumption. And if we can get to low manufacturing costs, which is also an important assumption. So all of the current perovskites in literature are not cheap. But if we go to cheaper manufacturing costs, cheaper materials, then we can get here. Yeah, this is sort of an assumption, but it seems realistic that we can get there. Efficiency-wise, perovskites have been getting very close to silicon on small areas. On large areas, we still have to get some work done, but I think hopefully we'll get there. But really the biggest issue is that silicon lasts around 25 years. Some people say even longer. You can definitely say that silicon lasts for decades, while perovskites, even the best reports are only around a couple of years, maybe a year. So that's really a big issue. One has to work on that. But yeah, I mean, you see there are different factors. So one idea is to bring them all together. One can use the LCOE. LCOE is the levelized cost of electricity. So essentially, it's just all cost divided by the yield. So it's a number, and you can calculate this number. I calculated that number for 2021 based on the annual PV benchmark report. So this is an annual report NREL publishes, and they publish a series of different numbers, which they get from solar PV manufacturers, but also like intermediate sellers. And so I've calculated those numbers, and I've been getting to 11.9 US cents per watt DC. And they reported the same number for 2021. So I calculated based on the input parameters, the LCOE, and got the same. And essentially, you can do then a back calculation, because assuming we get to the same LCOE, you can infer what efficiencies and stability a PV cell has to reach, assuming a certain manufacturing cost. So you can calculate that if you assume there's 3 different input parameters and sort of make a graph out of this. And this graph sort of summarizes for different architectures at different efficiencies, the necessary T80 lifetime to reach the same cost as silicon. So for example, for a rigid perovskite solar cell, if it would have a 25% efficiency on the module level, you see here that it needs roughly 15.5 years to reach the same cost as silicon. So this is sort of a parameter space which sees in how different efficiencies, different architectures have to reach certain lifetimes. And it gives you sort of a framework to know in which lifetimes you have to get. And the change is considerable with different architectures because different architectures have different manufacturing costs and different efficiency limits. And the big thing in this work, which we published, was that with flexible solar cells, you can save in the balance of system costs. And that's why flexible solar cells, while at the same efficiency, need to reach lower lifetimes, because you can save on those balance of system costs. So the installation becomes easier. You don't need the racking, and you can easily store it. So it's quite nice about flexible cells. So what I will talk about now is how do we get to those stable perovskite solar cells. So we know that we have to get at least 1 order of magnitude higher stability. And I've been working on it for a while. And the thing I can say with certainty is that the one thing which correlates the best with improving stability is changing the way you make your perovskites. So the moment you go away from like what has been sort of as established or grown over time is this DMSO route. And the moment you go away from that to different manufacturing methods, we have been getting a lot better stability data. And so one of those fabrication routes I've developed in my PhD was what I call a DMA route. So David McMicken and I developed that together during my PhD, and he was a postdoc. And so what is this DMA route? This DMA route, and what we do is we add 30 mole% excess of DMA chloride to an FA-cesium perovskite, which can be something between 10 to 70% bromide. That can also be DMA methylammonium iodide or dimethylammonium bromide. Then we put the solution onto a substrate. We solvent quench it with an anti-solvent like trifluorotoluene or a mixture of trifluorotoluene and ethyl acetate. And then we anneal it, and actually quite severe. So we anneal it at 170 degrees for 90 minutes in an oven. And so what happens is with this change is the moment we add this DMA route between after the first immediate annealing, the films are actually not black, but rather yellow, orange, or red. And these indicate polytypes, hexagonal polytypes. So for FAPI, one would call this the delta phase, but for us, it's it's the intermediate structure which we form before it goes to the final perovskite. And you can clearly visibly see it. And then only up on the second annealing step, so if you go to like 150 degrees or higher, the films start changing and go then into the cubic perovskite phase. And normally if you add the DMF-DMSO one with the FA cesium, you almost immediately go into the cubic perovskite phase. One of the big things which we have seen being changed in this is the orientation of the FA cesium film. So here you're looking at a 2D XRD, and you're looking at the cross-section of the cone. So the signal comes out, you get the cone out, and then you look at the cross-section of the cone. So this is the 100 peak, and the cross-section of that. And you see for FA cesium and DMF-DMSO, you have two maxima, which are slightly off from the initial. So they're at an angle of roughly 30 degrees. And then the moment we add the DMA, so it's 10%, and then with 20%, we see the alignment of the grains. And here's sort of like a schematic, which means that the unit cell in its orientation becomes oriented with the substrate below. And that means that you have a face-up orientation. So the 110 faces you the moment you look at the substrate. So you can imagine that the grains are more uniformly distributed. Another thing is that because we left out the DMSO, so we just use DMF, we obviously don't have any DMSO left in our films. So here we have some solvent NMR. This is in deuterated acetonitrile, so that's why you see this acetonitrile peak here on the right. For the DMF-DMSO films, even after annealing at 100 degrees, we find that there's a DMSO peak and the homogeneous peak here. And for the DMF-DMA route, we find that there's some DMA left in it, but no DMF, at least not in the solvent NMR. We didn't find that. And those devices also show better stability. So this is quite a large study. So this is just a stabilized power output. So this is an aging box, which is at 65 degrees or 85 degrees. It has a full phase. So this is aged with a xenon lamp. So it's a full spectrum. So it does have a UV component as well. And then we take the devices out to measure to the solar simulator and measure devices there. And then we add it back into the aging box. And here we see that we have quite a large number of devices. And the DMF-DMA devices have a T80 of 1,200 hours roughly at 65 degrees. And the controls roughly around 780 hours in the same conditions. And at 85 degrees, we see a lower lifetime, which we find to be quite usual. And there the T80 time for the DMF-DMA device is roughly 430 hours. And here on the right, you see the champion devices. So yeah, I have a little summary. This is Mina's summary, that it's a dog of my mom. So the DMA route changes the intermediate phase to polytypes. And then only after annealing, we go to the perovskite phase, which is face-up oriented. There's no residual DMSO, and it has higher stability under moisture, heat and light. So really all factors. So now I show a different fabrication route. I didn't develop this. That was developed by a colleague. It was developed by Benjamin. And I was helping Benny a lot. So that's why I'm talking about this route, because I was really heavily involved in this quite work. So what Benny did in his work is he had this solvent, methyl THF. It's a green solvent. It's a biorenewable solvent. It has a very nice vapor exposure limit compared to all the other nasty solvents we have. So it is a green solvent. And what we do is we have methylammonium iodide and lead iodide. And he adds the methyl THF, and it's an apolar solvent, so it's essentially just suspension. So the powders are still black. It's not dissolving the powders, but only if one adds the amine. If one adds butylamine, the reaction between the Bronsted activity of the amine and the methylammonium causes the precursors to dissolve. So you get a 2D precursor solvent. And then the moment we spin coat those, we get a mixed phase, a 2D perovskite, which is lovely red. So this is actually an image of this film. And then only after we convert it with the conversion solution of butanol and anneal it 180 degrees for 1 hour or 1.5 hours, we get the alpha phase of FAPBI3. So we find there was no methylammonium left inside it of it, and also very little butylammonium. And this route allowed her to make some nice devices. So here on the small area, you see that the devices reach the JV scan efficiency of 20.5 and a steady state efficiency of 20%. And here you see cross-sectional SEM in an NRP structure, but we also made them in a PIN structure. This is FTO, then the tin oxide nanoparticles, then the FAPBI3, a surface passivation, and then a spiro and gold. And the really surprising thing about this study was really enhanced stability. So I measured this on a Rigaku Smart Lab. It's a 2-dimensional XRD setup where I also have a heating stage. And this is measured in ambient air. So we exposed the films to 130 degrees in air and measured it for 9 hours. And then essentially monitored the 100 peak position over time. So here on the axis, you see the 2 theta degree angle. And here you see the 100 peak position. And then on the y-axis, you have the time. And then the intensity shows the diffraction, the intensity of the XRD. And the molecules, which are shown here, are a different measurement. They're from a TD-GCMS measurement. So it's a thermal desorption graph chromatography mass spectrometry unit. So essentially, we just look at what is residual in the films and analyze that. And we find that for the 2D to 3D, that the only thing which is residual is the butylamine, this butanol, butylammonium, to be fair, which is from the 2D phase. But we didn't actually manage to resolve that in the solution NMR. And then you see for the other films, you see the residual solvents. So for example, here we have FAPI with 4:1 DMF DMSO, which was annealed for 10 minutes at 150 degrees. And that shows some cimtriazine and DMSO and some lead iodide during this test forming. And then the moment we add the cesium phase, we see that there's more lead iodide forming, but we also find other solvents like DMF and the anti-solvent. And the really surprising thing, I think, is the fourth column is that also if you make MAPI, so this is not the 2D to 3D route, but another green solvent route with acetone nitrile, we also get a lot higher stability for that. So we found that essentially the moment you make perovskites with a green solvent route, so no residual solvents, we find that the films are significantly more stable. And so we measured the stability for the device as well. On the left is a bit more film stability. So those are optical images, optical microscope images. So this is of the 2D to 3D FAPBI3 film after 3,600 hours encapsulated in light at 85 degrees. And that's the FA cesium film. And here you see the grain boundaries more clearly. And those white dots are lead iodide pinholes. So they're thinner, but also lead iodide. And after heat and moisture, so damp heat, 85% moisture, 85 degrees heat, we see that the 2D to 3D FAPBI3 has also very little degradation. And the FA cesium film shows a similar degradation with lead iodide forming small little pinholes. And we also see that represented in better device stability. So our 2D to 3D devices were a lot more stable at 85 degrees at 1 sun. So TT80 was around 450 hours, while the FA cesium devices very quickly degraded. And in the damp heat, we didn't really see much degradation happening for the FA cesium. A little bit, not too much, but our 2D to 3D films even improved throughout the measurement time. So I have another little summary, just in case. So there's a little take-home message from Teddy. We're using green solvent, methyl THF, but it's also possible with THF. We have no residual solvents. There's no cimtriazine forming in those 2D to 3D FAP-BRF films, and we find a higher stability under moisture, heat and light. So yeah, and the last part, which is sort of a novel idea, we'll talk a little bit about my last work from my PhD, which is a dynamic passivation. So the idea here is sort of like it's a very different concept. Essentially, what we always make is we make our perovskite films more resilient to stress factors, but we never really like change it. After the fabrication, the films are made. We can't do anything about it. But the idea is here that if there are new defects forming, we can have a passivation which heals then those defects as they're forming. So this is a dynamic passivation. So it can passivate defects after the manufacturing stage, so during the operation. So if there are new defects forming, they can be healed. And most of the slides I will show you now is essentially just to prove you that we have indeed a dynamic passivation and this is working. So what is the concept? Dynamic covalent bonding. So that's, I'm not sure how much of you guys are aware of this, but this is an own field. And there's a lot of progress going on in this field of dynamic covalent bonding. So one of them, which they developed, is this hub. And you can use this dynamic covalent bond to make, here we've made some polyethylene urea, and it has a dynamic covalent bond and can essentially switch, so can switch between this state and the individual molecules. So this steric hindrance, this bulky substitute, weakens the carbon-nitrogen bond, and that causes the bond to switch essentially. So it always switches between the coupled and the individual components of those two. So we made essentially a Rubik's cube, so yellow and black colored polyethylene cubes, and then we stick them together. There's no glue or anything involved, and just by time, by holding them together, they form sort of a Rubik's cube over time because of the dynamic covalent bonds, which are then forming bonds between the different cubes, which I thought is sort of like a nice demonstration of those dynamic covalent bonds. And through the Hubler, so this molecule which we're designing, we also add a thiocarbamate bond, which shows dynamic behavior at higher temperatures. So the first one is a bond which is typically activated by water. So it's always between on and together, off, on, off, on. And the moment water comes in, it takes this away. And now the big idea we had is that we also add, with increasing temperature, we also want to have some form of healing. And that's why we have this thiocarbamate bond, which shows a higher reactivity at higher temperatures, which we added. So this is the molecule, the Hubler. This is the hub. And then we also have a thiocarbamate bond here. And the combination of both allows us to have sort of a dynamic covalent bonding under heat and moisture. And we also measured that. So here's an NMR in deuterated, with deuterated water. And essentially what happens is, because of the, it takes time for deuteration to take place. So over time, we would expect the hydrogen peaks to vanish the moment the deuterated water goes into the structure and replaces the hydrogens. So the hub over time, the signal vanishes because it more and more reacts with the D2O. And so that's a signal that the first reaction happens, the dynamic kinetic urea bond, and then we anneal it to higher temperatures at 65 degrees. So we increase the reactivity, and that's when the thiocarbamate bond, this one, slowly disappears because of the D2O. And it was sort of like a first sign that our dynamic covalent bonding is indeed working. And now we have a bit few more schematics, which sort of like show this in detail. So at room temperature, we have the Hubler, and this is sort of like switching on and off between those two different states. And then we have the water coming in, and it can react with the NCOS to then form NHAS and CO2. And depending on where it's sitting, it can react with different form of defects and bind to them and passivate them. So it needs water for the dynamic covalent bonding with that. And under heating conditions, it's a redox shuttle. So we have the TBD, we have the thiocarbamate bond, and then it has the CH group, and then iodide is coming, and it takes electrons from the iodine and reacts with the lead zero to form again lead, and the I2 gets reduced and then can go back into the lattice. And that's not a new concept, but someone has written a science paper about this already with europium a couple of years ago. But this is just another way for our dynamic covalent bonding to show how we can continuously heal the perovskite. So one proof for this is with XPS. So we looked at this lead zero evolution over time at 85-degree aging. So we aged some films over 1,000 hours at 85 degrees and measured XPS continuously on those films at 85 degrees. And you can nicely see how over time the lead zero shoulder is forming for the films without the Hubler. And for the films without the Hubler, we don't see any shoulder forming. So that's for us a strong signal that the thiocarbamate bond is indeed working as a redox shuttle. Another proof is here. So this is a convocal, this is a laser scanning microscopy setup. Or actually it's more of just a PL map really. And those images are not scaled equally, but the left one is scaled differently because the right one gets so bright I had to use different scales. And here we age the films under 40 suns for 1 hour under 40 times magnification. So you see that FAPI gets a little bit brighter over the 1 hour, but it's really the Hubler film which really improves in brightness a lot over the aging. And we summarized that in the paper. So here, so for the Hubler film, we aged it under sun. And then after the measurement, I went with the stage a little bit to the side so that in the middle, you can see on the left side the aged area. And then you see here the borderline area that's transitioning. So this area was not exposed to any sunlight. And then you can nicely see the change in PL, which was induced through this exposure of the light. And you can nicely see here, this is a cross section essentially through the middle, how the PL signal is a lot higher for the exposed area. And here for the control, we did the same thing. You see that there's only a very small improvement. And I was quite confused by this, why the control also improved. But there's actually a review by Sam Strength about this. And I think it has something to do with me doing these measurements in oxygen. And that's why oxygen is passivating those defects. And it's quite well documented, actually. So that explained this for me. Here we have some statistics. So here you see the pristine and then the photoluminescence intensity after the aging. So there's a very small improvement. But the pristine films have a lot higher luminescence from the beginning and then even improve more, significantly more with the aging. And this is sort of like an in situ aging. You see here has a drop very quickly in photoluminescence and improves a little bit over time. And for the Hubler, we also see this drop, but then a significantly stronger improvement. So here on the left axis, you see quasi-Fermi level splitting, which you can correlate with the PL intensity. And then on the right, you see differential quasi-Fermi level splitting of the maps. So that's between the first and the last map. And then you can associate sort of like an ideal VOC enhancement for the map. And you can see that the Hubler sort of like has regions of very strong improvement on the films where the PLs increases significantly. Yeah, and another experiment we have done to prove the dynamic passivation of Hubler is we have a DMF solution with iodine. So it's black. And then we add the Hubler to one of the vials and to the other not. And you see very quickly how the solution is turning clear because it's the redox shuttle again. And the iodine is reduced to iodide, it becomes clear over time. And then we added a lead pellet to both. So it's a very thin lead pellet. And this lead pellet is then steered. So this is the steering bar over time. And then because it reacts with the iodide, it becomes lead iodide. And that's why then it's turning slightly yellow over time. And control really doesn't happen much. And we also proved this in devices. And we find a significantly improved stability and efficiency for both PIN and NIP. So for PIN, we find we get roughly 25%, and for the control around 22.7, especially in VOC and fill factor. But also for the NIP cells, we find an improvement in efficiency of like around 3%. And yeah, we also get some good stability. So this is encapsulated, but stored in air in the Hubler devices. Quite stable for 1,000 hours, while the control very quickly degrades at the beginning. And in nitrogen measured at 85 degrees under 1 sun, we also see similar stability for over 1,400 hours. And this is some data I measured in Oxford. So this is at 85 degrees in nitrogen, and I measured 12 devices over time, and they improved. So I normalized it to the peak efficiency, the peak median efficiency at around 786 hours. Then after 2.5 years, the devices degraded to below 80% of the peak median efficiency, while the control devices reached that in 4,500 hours. So Teddy loves balls, I guess, just as we love stable perovskites. So summary, how we can get there. It's a dynamic passivation allows to heal defects after the fabrication. So it's a new concept. To improve the performance of NIP and PIN devices and increase stability under heat and moisture exposure. And yeah, here the papers I've been talking about. So the first one is a review in JMCA. The second one is a perspective in Joule. It's the cost calculation, and then a couple of my PhD works. And with that, I would like to thank Henry, my supervisor during my PhD, and Udo. I actually went to Monash for more than a year and was working there with him. And Michael, who was supervising me during my master's and internship. And Jianping Feng, he was doing the Hubler work with me. And he actually even came to Oxford twice. And David for doing the DMA work with me. And he also supervised me and really was a great help. And a couple of other people who were working very closely with me throughout the year. And my funding, the Marie Curie. And yeah, thank you all for your attention.